discussing two presentations from the physics seminar about quantum electronics and lasers at Stanford. One is Cheng, University of Chicago. He's creating artificial quantum systems, in particular Bose-Einstein condensates, which is a specific physical state of atoms that helps researchers mimic actual quantum systems at a scale that is a little bit easier to research than maybe other types of systems. And what he's trying to do, amongst other things, is use these artificial quantum systems and look at, simulate actual phenomena in nature, in particular cosmological phenomena such as the Sakharov Oscillations, Kibble mechanism, inflation. I'm going to discuss in detail what they are and how artificial quantum systems can help us in understanding this. The other presentation I want to discuss is about a quantum teleportation computer, and that is a quantum computer that is actually based on optics. So you have a manipulation of light based on modulation, frequency modulation, amplitude modulation, that mimics a quantum computer and mimics the effects of, let's say, a quantum algorithm such as Hadamard Gates and things along those lines. So the optical quantum computer is a possible solution to use photon modulation to mimic quantum gates and exploit parallelism such as entanglement and or interference. And the advantage of this is you don't need a chip, you don't have to do all this cumbersome physical transformations to get quantum state and coherence times. To me, this is a very interesting approach. I haven't heard of this as of late, but certainly makes a lot of sense. So you think of it like more of a software-defined quantum computer that actually uses real physics to mimic what quantum states are all about. So I'm not quite sure if I fully grasp what he's doing. The presentation was done by Akira Furusawa, so his English wasn't exactly the best, so it was a little bit difficult to follow, but he's from Caltech. He worked on the Preskill, so he's done a lot of work in quantum error correction, and I believe that that's really the key here. It's a software math-defined approach using laser and modulation to actually mimic quantum computers. This is not in the wrong podcast. It's September 25th, 2024. This is Krimdelgo. For the day, the fund is up 1.9%. The market is down 20 basis points. For the year, we are up 24.5%. The market's up 19.7%. We're outperforming by 4.8%. So let's talk about these two presentations. They're part of the quantum physics and electronics conference. So it's basically how lasers and optics and quantum can together offer solutions. And number one, I think Cheng from the University of Chicago, who's creating artificial quantum states, in particular Bose-Einstein condensates. So, and that that in itself requires laser cooling. So there's definitely one application of optical technology here. But the key is, in a more sort of global perspective, if you want to simulate nature, you can do that by looking at actual quantum systems. And once you have a quantum system, of course, you need to Hamilton engineer certain processes to transform that quantum system so you can actually learn something. And what Cheng is doing is exactly that. So he's first creating the quantum system, and then he's Hamilton engineering that quantum system to learn about certain effects. And in particular, what caught my eye is the quantum simulation in cosmology. So Sakharov oscillations are early oscillations in the universe that were created and that are supposed, theoretic, this is theory, this is conjecture, that they are driving the distribution of matter in the universe. And all of another thing is Kibble mechanisms. So this is a structure forming in phase transition of the universe. And inflation is a theory of the universe that, there's something 10 to the minus 32 seconds after the Big Bang, the inflation kicked in, and that created a couple of things that today we observe. For example, the uniformity in the universe from one side to the other. Given the size of the universe, it is highly unlikely that those two sides, communicate with each other to keep themselves in uniform. So it's more likely that they were together at some point and then expanded through inflation. Now, all of these effects are conjectured. Of course, we can't go back to the Big Bang, but what we can do potentially is simulate the Big Bang and simulate the quantum effects that happen right after the Big Bang and help us understand what should happen based on the laws of physics and actually based on what we observe. If we're able to construct a quantum system that is pure of any influences other than the quantum system's influences themselves, and then watch it evolve, and maybe Hamilton engineer certain evolutions, or we can even have some sort of in parallel iteration to try to learn from those distributions what might have happened right after the Big Bang. So if we could do that, we could potentially we could validate our theories or develop new theories about cosmology. So this is the first presentation, and I think what's interesting here is, of course, that we have an application of quantum systems or quantum mechanics, but really quantum systems. This is physics engineering, right? You're not really coming up with new quantum theories. You're just trying to create a quantum system as pure as you can to then study cosmological effects such as Sakharov oscillations, Kibble effect, and inflation. So this would be the first presentation. The second presentation I want to talk about is Akira Furusawa. He's a Caltech alumni now at the University of Tokyo. And what he was talking about is laser-driven quantum computers. So the way I understand this is that you create sort of a software-defined quantum computer using lasers. And because you're using light, you can actually you can do the two crucial things that the quantum computer allows you to do, which is entanglement and superposition. So you can do at least superposition for sure. You can do. I'm not quite sure about the entanglement side of things, but you can do that with frequency modulation, amplitude modulation. You can then apply quantum error correction, and Furusawa actually has worked on that. But what's really most striking about his presentation, or most interesting in my opinion, is the fact that you can replicate quantum gates with software-defined optical computer, and therefore you can turn that into a quantum computer. So that's really what's so exciting. Now, I think Furusawa is actually about to launch a startup, so there is a possibility here of commercial use. What's interesting, of course, is also that you're not confined to very short coherence times. You have potential for many, many logic gates because you're using classical physics actually to mimic the quantum computer. But this is not sort of the stuff that IBM is doing in the cloud, where they're using classical computers to mimic quantum gates or mimic quantum evolution or something like that. What they're doing is really using software-driven modulation of light to introduce quantum type effects such as interference and entanglement, which then allow you to actually implement Hadamard gates, for example, and other types of quantum-only gates, and therefore use quantum algorithms to do what quantum computers in theory can do. So this is the conjecture. And again, I'm definitely not up to date on the theory of these things, but I would say that there is something here. This is an interesting thing that I would like to follow closely. Thank you.